defined in sky coordinates. So the sky region is the one that I've defined before the circle. As you see in the second line, you have to pass as a WCS object. That's because the containment test behind the scenes is also made in pixel space. So this is actually this is basically just a convenience for you, so you don't have to convert everything to pixel coordinates and then do the containment operation. And then, as I said, at some point we also want to have real sky regions, and then you can test for containment in sky coordinates. So, I mean, for a circle is straightforward, I guess. You just test, if the separation from the center is smaller than the circle radius on the sky, but then we also want to have this for polygons, for example. Okay, another thing we have are masks. So if you have a given image and pixel regions, you can convert it to a mask containing floating point values between 0 and 1, meaning 0 no overlap and 1 complete overlap. And there are several methods how you can compute your masks, center, exact, and subpixels, and you will see on the next slide examples for each of them. So with the exact method, you just check is the center of a given pixel in the region or not, and then you say 1 or 2, it's 1 or 0, it's inside or outside. And if you want to have more precision, depending on what field you are, you might have a good angular resolution. So you can use this exact method, which computes the exact overlap between the circle and a square pixel using some geometry. And there's also this subpixel method, which basically splits each pixel into an array of subpixels and does the Boolean test for each of them. And there's one other thing called bounding boxes. So of course, if you have a 1000 by 1000 pixel image and just a very tiny aperture somewhere, you don't want to have a Boolean mask that is 1000 by 1000 values, and therefore the masks are just stored in the minimal array that contains the whole region. And in order to know where this array is on a huge image, there's this bounding box, and that tells you exactly that. So, for example, here, if you in this image, so you have defined your aperture as a circle pixel regions, and okay, so then there's some plotting that I will come to later. But the interesting line is the fourth to last line. So the mask has this B box attribute, which is a bounding box, and then if you plot it on the image, you see this white rectangle. So this is basically the idea behind bounding boxes. Okay, another thing that is implemented are compound regions. So I guess it's quite self-explanatory, but if you have two regions, you can of course ask, so what is the intersection of these regions, or the union, or the symmetric difference between the two, and then for all these operations there, we've overloaded these operators, so the AND pipe and this roof thingy, which I don't know what it's called actually. And so what is this useful for? So this is an example how you define such an intersection. So you have defined two circles, and you just define the intersection like this, and then you see that it is now a compound sky region object consisting of these two components. And so this is an example what this can be useful for. So the blue dots are just sky coordinates, and then for each sky coordinate you can ask, is it contained in the compound region or not? And then you see with the XOR operation in yellow that of course the points that fall in one or the other region are marked, and then if you have connected them with AND, then you see that only the ones that fall in both regions are marked. So yes. One comment about lists. Those of you who have used phototils probably know that in phototils you can represent an array of apertures as basically only one circular aperture object with one radius and an array of positions. So this is not possible in our package. In this package you have to, each object can really only represent one region. And if you want to have a list of regions, then you have to use some Python containers to represent that. So, for example, in this example, you define this list of regions by looping over pixel coordinates and then defining a pixel region for each of them. So I'm not sure what that means in terms of performance. So I guess the phototils guys had a reason why they implemented this list like that. Yeah, but we decided not to. So I don't know. I'm not so familiar with the discussion behind this, but I guess someone else is. DS9, as I said, so the one key feature is to serialize region objects to DS9 strings, and then also be able to read and write DS9 files. This is also implemented. So if you, for example, have a DS9 string like this, then you can use the DS9 parser from the regions package and cannot read all DS9 regions. There are some, for example, pandas or elliptical pandas that we cannot read, but no panda, sorry. Yeah, so I guess one question is how to read the DS9 string, which is one issue. But then also, if you have, for example, an n annulus, so in DS9 you have this region that is basically an annulus with n radii, but so it's not really clear what this is supposed to mean in terms of a region. So what is inside, what is outside of an n annulus. So we have to come up with a solution how to support these, or just say, okay, we cannot parse them. This is one thing that we've worked on this week. It's a comparison between the region parser that we have and the one that is implemented in PyRegion. So we have a couple of example files to test, and as you see that if you look at the fourth column, so this one, that for most of the files we cannot read all objects, but only like half of them or so, and whereas PyRegion always has 100% coverage. But as I said, we are a little bit better in terms of speed. So if you look at this, for example, which has 100% coverage in both, then we are really much faster than the PyRegion parser. Okay, so I think I'm running out of time. But so one other thing is plotting. So you can plot a pixel region by calling the aspatch method on it, and then it will return you a matplotlib patch that you can attach to an axis object. So this is an example how to do that. Yeah, I mean, it's just straightforward, I guess, how to plot regions. And then as summary, so the package now is in a state that I guess it can be very useful for most of you. So you can create regions in a script as Python objects. As I said, regions are defined in pixels. You can instantiate them with sky coordinates or pixel coordinates. You can create composite regions and test for containment by transforming into pixel space. You can create mask for all pixel regions, and you have DS9 IO and then read DS9 file and make nice plots. And so yesterday after the hack, I didn't want to go to sleep, so I played a little bit with the DS9 GUI. And so this is actually a DS9 file I've made in DS9 and then read with our package and plotted it.
Thanks for the nice talk. I wonder if you, for example, define a circle on the sphere, so and then translate this to pixel space, maybe in some really ugly projection, then it may be well distorted.
Yes.
So how do you deal with this? I mean, if you have a circle in world coordinates, it won't be a circle in pixel space, but it will be a very ugly shaped something. So how do you do it internally?
Well, so basically, I mean, you mean how do we do the transformation?
Yeah.
So at the moment, not yet, but I think you have an idea how to do that, right?
Yeah, so well, we did have it. We removed it yesterday temporarily, but we'll be back. We just transform it to a polygon instead of, we don't. So a circle, a spherical sky circle, transform to a polygon, and the user can specify how many points they will sample along the edge of it when they're doing the transformation.
Okay, but you don't have a utility function that determines a good number for.
Not yet, but that's. I mean, that could be done. Yeah, there's no reason why that couldn't be done in the future.
And
wouldn't a lot of cases be handled by just transforming into an ellipse?
Yeah, I mean, so originally, in the original API, what we had is you could transform it either to a full polygon, to an ellipse, like the kind of approximation or the distortion, or a circle. And yeah, so we'll add those kind of modes back to the, yes. I mean, there's sometimes where you can approximate it by an ellipse.
Right.
Yeah, so.
Sorry. So on this question of they can only be scalars and not arrays.
Mhm.
I mean the motivation for the photoutil side of things is that you do some sort of photometry, aperture, PSF photometry, but you might have like 10,000 of them in one image,
Mhm.
and you don't want to have 10,000 objects because there's a ton of overhead in working on that. So do you think what do you think is the best solution for situations like that where you do have 10,000 regions and you want to do something with them?
Yeah, that's a good question. So I mean, I personally have never encountered this because I have maximum like 5 or so in gamma astronomy. But
That's more than 5.
yeah, okay, but that's just
Like
that's for illustration. Yeah, yeah. I don't know. I mean, I guess at some point there will be a trade-off between efficiency and whether or not you want to define a region like this, like as an object. But do you really think it will be critical to have 10,000 of these?
Oh, absolutely.
Okay.
I mean, they don't necessarily have to be in that object, but I mean, most there are tons of practical optical use cases where you have tens of thousands of sources in one image all the time.
Okay.
Yeah, people will want to do that.
Okay.
So, this seems like it's going to be essential in the coordination between regions, in the coordination between regions and photoutils.
Mm-hmm.
This is going to be like an essential piece is figuring out.
But couldn't you have like a helper object basically that holds a list of sky coordinates and the radius, and then just in a loop just creates objects on the fly to do the operations?
Yeah, maybe. I mean, so that's exactly what I was asking.
Okay.
Maybe that's the answer.
That was the idea before. We've coordinated this in terms of photoutils, and the idea was you can keep a region object and it's mutable, so you can change the values inside it, you can change the coordinates on the fly. But you never need to actually have 10,000 regions at the exact same time, because when you're doing photometry, you're just looping over the sources. So, yeah.
Cool. Well, let's thank Duncan again. Hey.
No.
Generic.
Gonna go the right way around. Way.
Increase the resolution of your output.
Can I increase the resolution of my output? If I can work out where my thing is. Technical difficulties. Is that better?
Yes.
Okay. All right. So, my name's Duncan. I'm from the LIGO Scientific Collaboration. I work at LSU. I'm going to give a basic overview of kind of a little bit of gravitational wavesy science, not very much, and a little bit of Python, not very much. So there's a good chance you might know all of this, so you've probably got lots of email to check. Otherwise, there's some nice introductions to the fact that LIGO has data, and you can download some of it. It's kind of the opposite problem to a lot of people here who work with open data, so they're not really sure about releasing their code, whereas LIGO, all of the code is public because none of you can get access to the data anyway until we publish it. So gravitational waves in one slide. I'm not going to go through this in a lot of detail. The main points are that gravitational waves are a thing from theory from 100 years ago, almost exactly. And we built a whole bunch of kilometer scale laser interferometers to detect them. There's 2 in the United States at the moment. That's LIGO. One in Washington State and one in Louisiana, so they're quite far separated. There's one in Europe, which is called Virgo, which will actually be coming online in something like 2 weeks, so it's actually very exciting. There's one in Japan that's being constructed and should be online maybe in 3 years, 5 years, something like that. And then there used to be 3 in the United States, but in order to improve our sky localization, they decided to move one of them outside the United States. So that will actually be built by the Indian government and maintained as kind of part of LIGO, but in India. So that will come online in 5 years, 8 years, something like that. They haven't actually started building it at all, so timelines are a bit iffy. The basic idea is that a passing gravitational wave causes a differential phase shift in the 2 arms of our interferometer. So when we recombine those beams, we get an interference pattern that directly imprints the energy from our gravitational wave. So we can read that out in the time domain and reconstruct our signals. So we are doing transient time domain astronomy with very, very short signals. The big problem is that larger phase shifts caused by the mirrors just shaking are easily caused by things like seismic noise. The actual Brownian motion in the objects themselves is much larger than a typical gravitational wave signal. Radiation pressure, quantum noises, etc. And these all drown out our gravitational waves. This is gravitational waves on one slide, slide 2. Basically, it's a big, massive series of approximations, but it turns out that it does actually work, and people believe us when we publish these things. Most of the time. So this is figure 2, I think, from our detection paper, which is linked there. Basic diagram of anyone's laser interferometer. This is not specific to LIGO itself, but we have a laser source, beam splitter, 2 arms, so it's a kind of Michelson interferometer, but we have various other mirrors that we use to build resonant cavities, which allow us to do much more sensitive signal extraction and kind of signal multiplication. So the beams resonate in the arms, which means we can increase the relative phase shift introduced by a gravitational wave so that we can actually detect these things. This is the United States, so this is LIGO Hanford up here, LIGO Livingston here, so they're as separated as we could reasonably do it, which gives us a 10 millisecond light travel time, which is in principle, the largest time offset between a signal of a gravitational wave, which may be nice and simple for you, but it's quite a good example. This is a binary in spiral, so we have 2 black holes. This is actually a model of the signal we detected. So they coalesce. The green lines are the strength of the amplitude of the signal. It dissipates in all directions. At some point, the Earth will appear over here. But you see it's weaker and weaker and weaker. It was quite fun. The top is our actual data once anyone else. And at the same time, we released 11 other papers onto the archive, which are all of our companion documents in terms of calibration and parameter estimation and all this kind of stuff. So we had everything lined up quite well. And these are 2 of them, which I think are most relevant for this group, which is the astrophysical implications of GW 150914, which is our signal. We do a kind of a GRB style naming convention. The second one is the localization and broadband follow-up, which is probably the most interesting. We've just heard about sky regions. I'll have a couple of figures from that in a second. And then this third one is interesting if you want to follow our development as a field. This is our observing scenarios document is what we call it. And it goes through our relative sensitivity in the 5 years into the future and what that means in terms of sky localization accuracy and that kind of thing. This is we had thousands of observations in very small chunks because that's the instruments we have. But yeah, lots of people were looking at this, but the problem is that this is what you see. It's a binary black hole coalescence, so it's not exactly EM friendly. Our kind of most famous source target is binary neutron star, in which case it will be very interesting. So it's quite a nice test that we can do all of this. We release signals into the wild within I think it's 20 acquisition, but we have 2 different searchers. They're both written in Python. These are using millions of CPU hours. The fact that you can do this with Python on the top as the user layer is quite nice, but all of the hard stuff underneath is C or whatever, but you can go and read the code. Also parameter estimation, EM follow-up, kind of our notification system, and then detector characterization, which is what I do. This is all Python stuff, so it's used kind of everywhere, which is nice. So in terms of detector characterization, a generic problem is that a lot of our code is written by very, very smart people who aren't very good at talking to other people. So the major problem is usability and documentation, which is kind of no change there. The technical problem is that LIGO has one single output for data analysis purposes. We have our gravitational wave readout channel, but we have 100,000 other signals that we acquire in real time continuously that are kind of our instrumental control or environmental control. So doing any kind of correlations you need very usable tools to read lots of data and to do all of these things, so that scientists don't waste their time copying and pasting code, which normally means that they don't try and understand it because they don't have time to. So my job is basically to try and write code that other people can use that makes sense, and I hope I've achieved some of that. So this was kind of my hack for yesterday, is to do enough work to make sure that this command actually works, which it didn't yesterday. So GWPy is my thing. It's a Python package for gravitational wave astronomy, which sounds kind of generic, but it's just a nice way of loading data and plotting data and doing kind of simple signal processing. It inherits a lot from Pi, more in terms of kind of philosophy of the way the code is presented, but also uses a lot of the input-output routines and that kind of thing. You go to the website. The idea is it provides object-oriented methods to access data. So you can run this on your laptop, and it should work today. The idea is that you install GWPy. You need HDF5 to actually read the open data files from LIGO. But if you run these 4 commands, you import the object, fetch some data. This communicates with the LIGO Open Science Center archive, downloads actual data, and you make a plot and you show it, and you end up with this, which is not perfect, but it's a good start. So we have time in seconds. We've downloaded 32 seconds of data. It's kind of grungy, but if you add 25 more lines with some basic signal processing and a lot of matplotlib formatting, you get this, which I think is really nice. There's a link there. You can go and see the full kind of worked example. You can recover gravitational wave signals on your own, on your laptop, without having to be a crazy wizard. Yeah, more GWPy examples. This is kind of a screenshot of the web page. That's the link, but there's 20 examples, 25, whatever. They're all, the idea is that they're worked nicely. This is a screenshot of one of the pages. It's generating this image, which was kind of our detection image. Import your object, download your data, do some transform, make a plot. There you go. It's designed to be easy. Now, this is really picking up inside LIGO because we have access to our own data archives, and we can do a lot of this, mainly because it's really easy to use, which cuts out a lot of the problem. For you guys, the more important, more interesting thing maybe is the LIGO Open Science Center, which is an NSF, National Science Foundation idea with a bit of funding to start with, but they don't have any funding anymore, to release our data. We were required by the National Science Foundation, whenever we publish a gravitational wave detection paper, we publish the data that we use to make the paper, which is a fair enough requirement, but it's a big kind of infrastructure commitment to be able to host these things in a discoverable way, but it's not something that astronomers haven't done before. So we have a subgroup of the LIGO lab doing this. Files are hosted in GWF, which is a file format that was invented for LIGO and only used by LIGO and Virgo. So you guys have no idea what it is, which is fair enough. So we also do HDF5. If you go to losc.ligo.org/events, you can see all of our events, all 2.9 of them. But then the S6, which is 2009-10, we have our full data archive for our full gravitational wave strain for that, which is not got any signals in it, so don't do it. But we're getting into things like event catalogs, which sounds great to us, but it's kind of normal to you guys. So this is the kind of thing that we could fit into something like AstroQuery, where you can download GW event catalogs with all of our parameters, all of our sky localization things, parameter estimation, and all that good stuff. The idea is that the GWPy package, the API, trivializes the way to download that. Obviously, AstroQuery would be more open community way of doing that in the future, but it greatly increases the outreach potential when you have good code that's easy to install and easy to run and open data. So for gravitational wave astronomy, this is a real step forward. That's all I have.
So with the data sets you're downloading, are you downloading a bunch of noise streams along with the filtered out data, or is it just the
So for now, all we have released is it's minimally filtered strain, like gravitational wave data. So it's a single time stream. So there's a single time stream of our gravitational wave readout plus a state time stream which tells you whether the instruments were actually operating or not.
Okay,
We have
so-
not released any of our, what we call auxiliary data, like our instrumental control signals, but we are working on a way to conveniently release all of our environmental data, which is probably of more interest.
So, you know, you showed that the GWPy, yeah, the GWPy documentation there, and you know the great amount of functionality there. But then I started twitching because I realized all of the data structures you were showing there that appeared to be unique to GWPy are similar to data structures that exist in SunPy. We even saw talk about the SunPy
Yes.
time series, AstroPy objects. Are you hoping to unify these, and this is a starting point, or what is your?
So the GWPy time series object is a subclass of the AstroPy quantity array.
Oh, so this is already building on.
So yes. So I hear a lot of people talking about AstroPy affiliated packages, and I don't really know what that means, but maybe this is
That would
a
be
thing
a
that
great
we
time
can
to talk
do.
about that.
Yeah, so I did have a talk with Alex about the idea that SunPy has a time series, like same characters, everything. They're kind of different, but there's no reason that they couldn't be merged at some point. This is why I am here. LIGO people tend to talk to LIGO people and don't talk to other people.
Well, now that you do astronomy, you should talk to astronomers, right?
But I'm a computer scientist.
So the data you can download in your package, is this really raw data, or how much pre-processing was involved?
So the event data, I am pretty convinced that the only thing that was done was downsampling. So we acquire at 16 kilohertz. You can actually download that 16 kilohertz record as well, but we have a 4 kilohertz record, so that it's much less data. The signals only go up to, well, this signal only goes up to 500 hertz, so you don't need 60 kilohertz. So it's minimal filtering in terms of hiding things from the public.
And the hardware in the instrument doesn't do anything? I mean, how do you extract the signal? If you have some CCD, I don't know, to measure the interference patterns.
We have a single photodiode which records our readout. We do the calibration into strain using other parts of our instrumental control signal. The strain is what we have released, not the raw photodiode signal. So what we have released is really what goes into our data analysis. If that answers the question.
With GWPy, can you also access like the data analysis stuff that's written for LIGO, like the waveforms?
So not with GWPy, but with the easiest one is probably a program called PyCBC, which is our compact binary coalescence, and that's the actual data analysis infrastructure. And there are hooks that you can translate objects from one to the other. So I do have an example, I'm not sure whether it's live on the website yet, of downloading data with GWPy, doing a single line translation into this other package's object, and calculating signal to noise ratio using a template, which is kind of the actual analysis. So that you do have to install something else, but it's still pretty trivial.
Any other questions? Okay.
Sorry? Oh, yeah.
Alright,
Alright.
so next up is how slow are your loops?
Yeah. All right, so hi everyone. I'll talk about how slow your loops are, but I've taken the leverage of being the last talk on this conference. So I've tweaked my talk in between, all the hack stations, and so that I've decided the tone of the talk. So here's how it's going to be. I'll first talk about the things I will not talk about, because when it comes to optimization, and I haven't used the word optimization specifically over here, we can discuss this like for days, because it's like a huge topic, all right? So there are a lot of things to take into consideration, but I'll just mention them, and just some of them I'll just give some links to some talks so that you can just further investigate yourself. Some of them are like talks. The stuff I'm trying to point out over here and try and measure them. I'll show how to measure them. But first and foremost, I'll just start with the name of the talk. It's how slow are your loops, not how fast are your loops. That's for a reason, because whenever we just crunch in some numbers, we expect the results. Sometimes we just get the result, and then since we already have the result, we like to go on with the science, but then we don't realize how fast that was. But if our code is slow, we just crunch in the numbers, we wait, and then we wait, and then we wait, and then probably something happens very late, I don't know. But then you just start asking, wow, that was slow, so how slow was it? So usually we ask the question how slow it is, not how fast it is. So just, if your code is fast enough, don't try to improve it. If it's fast enough for you and for your users, just leave it like that, it's good. And the other thing is, how fast are your loops? Now, the loop, I mean, it's just, it could have been named how slow your program is, how slow are your modules, how slow are your classes, or whatever, but loops is because we do a lot of iteration when we do scientific programming, and we do them in loops. So that doesn't have to be like the bottleneck of your program, of your software, but usually they're like the usual suspects. So if you suspect something that is going slow on your program, just look for the loops first. All right, but it doesn't have to be the loops, but it's probably the loops. All right, and just to be clear about the root of all evil, like, you can know your process is slow if you have like if you're processing live data like this talk over here, it's like a video stream, but if you want to process it live and then just feed it out live so that you can, I don't know, do some image processing on the talk, then if your code can't keep up with the live feed, then your code is slow. That's obvious. But the other part is that if you're squeezing in hobbies when you expect your results, then your code is slow, and you're not doing fair to your hobbies. Like in this example, I believe we have a professional fencer here, right? So if you practice on your fencing skills while you're waiting for the results, A, your code is slow, and B, your fencing won't get any better. So don't practice your guitar skills or whatever in between when you expect your results. So the most obvious way to fasten up your loops, let's say, is of course to write better algorithms. Now this is like the most cliche example, but we have to start with this. Let's say I want the sum of numbers from 1 to n. What do you do? The most, way is like you just run a loop, you just append the numbers, and then just add them together and you get the result. And the other way is of course to just calculate n times n plus 1 over 2. Now this totally depends on the nature of your problem, so it's not easy to talk about, so I will not talk about this, but the first thing you should take into consideration is using better algorithms. And the second thing is just to use mathematical approximations. So this on the top, you see, this is like the Morlet wavelet. So you don't have to know what that is, it doesn't matter. But in a paper, Foster presents an abbreviated Morlet wavelet. So if you're using this Morlet wavelet in time series data analysis, he says, if C is very small, by very small I mean 0.02, then a term drops, okay? And usually in time series data analysis, that C is very small. So you don't just take that into consideration. So just calculate it, which is called the abbreviated Morlet wavelet. Now, this is called, you won't get the exact same result, but it will be good enough for you, hence the name approximation. Okay, so just keep on using that. And the other way is using optimized compilers, especially for Python, but this is like that should take like ages to talk about, and I think we have some people using Python over here. We can discuss that later, but if you're just a novice in Python programming, you don't have to take this into consideration, and it will get harder to distribute your code because not everybody uses Python or Numba or whatever, but using optimized compilers, just-in-time compilation, or I don't know, C types in your code, that would help, but I'm not going to talk about that either. But there's a good talk about using optimized compilers. Now, this guy, he wrote a program that processes the elections of India, which is a very populated country. So he wanted to speed up his code very fast to an exam. And this talk is quite long talk, but he talks about various ways to optimize your code. Not only using optimized compilers to do that, there's this program called DCRow, and that is like the de facto program if you want to manipulate raw images, because some guy hacks them. People just send him raw images and he just works his way. It's like a magical thing. Nobody knows how to do that, but the source code is all open. It's a pretty cool tool. And he has his reasons to not distribute it as a library, so it's just a standalone program. Okay. But the output result is usually like a net PBM file. And I want to preserve like the bit ratio for that. So by the time a Python imaging library did not support 16-bit images, so you just had to work your way around. So the thing this program does, wrapper does, is actually get the input to DC raw, throw out a net PBM file, and then just read it back again, and then just pass it to PyFits. It's a rather complicated way, but it works. And I've just put this code onto GitHub, and a lot of people forked it and used it in their dissertations, even though I believe this is an ugly hack. And I never improved on it. Like it's been 6 or 7 years, and it's still like the very same version, but people still use it. Until like, I don't know, a couple of years ago, some guy mailed me, said, oh, I'm trying to use your code, but I want it to be real fast, and there's probably a bottleneck. I couldn't hack into it because I got lost in the code, he said, even though it's fairly clear, but whatever. And he wanted, I mean the writing of the code, not. So he just wanted to convert 1,000 raw images into 1,000 FITS files, but very fast. Okay. Now, if you look at it like this, the bottleneck is obvious because you just throw in the output of DC raw into a hard disk and then just read it again. So there's you do 2 times input and output. So you could just hack your way into it and just make that all in the memory. But if you don't know how to do that, it's just simply take leverage of your operating system. So sorry, I just missed this part. Meredith gave a perfect talk about sharing your code on GitHub will prompt spontaneous collaboration even if you're unfinished messy code. So this is like a great example. My code was very messy, but it helped a lot of people. So just put it on GitHub no matter what. Anyhow, if I've just mounted like a temporary file system in Linux, which actually looks like a normal file system, but it lives in the RAM, you just get rid of the input-output for the HDD for intermediate files. Okay, just a simple, quick hack. But if that's the right way to go, then your quick hack turns into like a Frankenstein, and people can't read through it. It'll get even more complicated. But if you just need to get it through fastly in a single night or whatever, you can just work your way around using tools that are already provided from your operating system. Now, just a simpler example would be just counting the lines of a text file. Let's just take a step back. Now, according to a thread on code, and it turns out that pure Python code was faster, but it was just 18 lines. So probably, calling the subprocess for only a small amount of calculation is, expensive. So what if my text file was huge? I had like 500,000 lines. Then in that point, calling the word count, taking leverage of the operating system actually helps. You got like 4 times faster. So if it was like not 500,000 lines, but more than that, it would be even faster. So you should measure your algorithms, you should measure your techniques and find out which is more suitable to your problem. So that brings us to measuring time. We want to measure time. We want to measure how fast our functions are, our methods are, or whatever. So how do you do that in Python? Now there's probably most of you guys know about this, but there's something called time it magic. It doesn't have to be magic, but using IPython or Jupyter notebooks, you can just time it and give it a function, and it'll just run it over several times and just give you the best results. If you don't use Jupyter, you can just simply use it like in any Python code. It's just a simple module. Now, you can also specify how many times to actually run the loops, or otherwise it'll just determine the number to run it after the first loop so that you won't wait that long. Okay. So in this example, I've just run the count huge lines and just got 84.7 milliseconds per loop. Right, that's the best result. Now, that is, of course, that depends on your hardware, but you can just measure them and get the difference between if you're still using the same hardware. So, and you can also output the object, time it to get a t, and then just get all the runs, the loops, repeats, best, worst, whatever. You can just do a lot of calculation over there. Another way to get measuring time is using the line profiler. Now, this is a very cool tool. Profiling line is like you have a source code and you want to know how long it takes for each line to execute. Now, line profiler does that. It's fairly simple. You can just pass in your program, and it'll just give you an output like this. Now, here you can see which line takes longer to process, and you just compare them between. Okay? I'll just skip this part because it's fairly. It looks complicated at first, but it's not that complicated. You can just check them out. And there's also another tool called Memory Profiler, and this just gives you like how much memory you use in every line. So that would also help. But the thing is, what we want to do is actually check what's under the hood, because if you call some functions or do some stuff, you get what line processes slowest, but you don't know what's going underneath that line. So you want to just check under the hood. So here are some very simple tips I want you guys to remember if you run into like a bottleneck in your code. So always, if you can, use built-in functions. If you don't know what built-in functions are in Python, they're just like over there. You can just read it from the docs, and it's fairly simple. So built-in functions are probably the fastest way to go. If you can, go with them. All right. There's something called function call overhead. Actually, this goes for every programming language, but it is like fairly big for Python. So if I just run a loop and then call a function in that loop like several times, it'll take, in this example, 1.7 seconds. But if I just directly call, do the calculation without calling the function and then another function, then you just get like a speed up. So Guido van Rossum himself also says that function call overhead in Python is bigger than a for loop overhead. So you can just check out this blog post down there. It's written by Guido, and it's a cool blog post. I'll just skip bytecode disassembler. This is you can just read on a blog post over here. That's also the talk is in Google Drive as in PDF, so you can just when you can. So if your function actually returns a list, use list comprehension in the favor. So that would be like a very good speed up. Like in this example, it gives you like a 15% speed up. All right, just wrapping it up. Okay. There's a cool talk about generators. If you don't know what generators are, Ned Batchelor has a very good talk. You shouldn't learn about generators, but if they're fairly complex too, just strict with a string, arrays or lists, and then you can just convert your code to generators using generators, because iterators, generators, and iteritems, they can get like complicated terms, but it is fairly good practice. Now, I'm probably out of time, so I don't want to run through this example, but this is a cool example. You can just look through the slides and just say, if you want to parse date, which we always do in astronomy, apparently, you can just use different techniques, and then in the end, here you get more than 80 times faster just using like an ugly code like this. All right. So we don't use the date parsing standard tools, but you just parse it all through, but that actually works, and you get like more than 80 times faster. I'll just, since I'm out of time. Okay, now here's something you shouldn't do. So going local, using local variables or local functions is really fast, but here's a good example from Sebastian Rutowski's talk. You should check that out. He gives 17 tips about speeding your code in like these native ways. It's pretty cool. Now, here you calculate the squares of a lot of numbers. Now, down there, he actually speeds it up by just, instead of using the output.append, instead of just using the output.append, he just points it to here and just use append. But that can, really get complicated when you're reading the code. Okay, so if your code, it's really long, people can get lost. What append is this? What is it appending? And stuff like that. But if you really need to speed your code up, you can do this, but use it with caution. And of course, use NumPy. This talk is not a tutorial, but it is to convince you to use NumPy and Pandas. All right. If you want to get convinced, you can just, Jake Brunner plus talk. But use it with caution because, remember the guy I talked about, the Indian guy, about the elections? He proves some points that in some circumstances using Pandas or NumPy can actually get slower, so don't take that for granted. So just to wrap it up, don't over-optimize your code, time it and profile it, use line profilers, use time it magic. When working on your loops, always start with the most inner loop to optimize, to work on it, because then you can get things complicated. And consider list comprehension generators and NumPy arrays, and take leverage of your operating system. Stand on the shoulders of the giants because they already worked on those problems that you've encountered. So, a little bit out of time, but thank you.
Questions?
So it seems like in a lot of these examples that making your code faster makes it harder to read.
Well,
And
I've skipped like this example. Actually, this example gives you like a 10% speed up, and it is PEP compliant. So instead of using A equals true, just use if A. But I mean, most of the examples, yeah, you're right. It makes your code less readable. Exactly.
so do you feel like this is the kind of thing you look at when you find yourself practicing your hobbies while your code is compiling, or are some of these practices you try and implement as you're writing your code?
Well, what I do is like I write it like in the most readable way first, and then I just work my way into optimizing them. And if I somehow get happy with the optimized version, but it's really unreadable, okay, I just leave it like that, but give like a whole either docstring or like comments of the actual original readable version, so that this black magic down there, it actually does this, but this is way more faster, so I just leave it like that. But I mean, it would be still harder to improve that line, but it would help people.
Any other questions? Okay, thank you again. Yes? Yes.
Cool. All right, everyone. It's time to cheer for all the hacks that have been happening yesterday and overnight and this morning. And so we're gonna start. I think. Do we have this thing? Does this work? Or is it easier if I just plug in my laptop?
I emailed it yesterday, it's on Twitter, it's in the chat. Oh, it's the Thursday document. Yeah, because we did the stuff on Thursday. It seems silly to like copy paste for.
How long do we have for this, Brent?
Yeah, 11:15.
All right. Sprint summarizer, 2 minutes. Otherwise, you won't get coffee. So, if you haven't put your stuff in there yet, do so as just append it to the end, and we'll get to you. And we'll just go through a thing. So, AstroPy velocities. Who would like to say something on AstroPy velocities?
Adrian?
You successfully did something.
You successfully did something. We spent a lot of time talking about continuing.
Is there something I should click on to show?
No, not really. I could plug in my laptop to show a test passed, but that's not particularly interesting.
It's a hack show and tell.
Well, I wasn't prepared to go first.
We're telling.
Yeah, that's
okay,
right.
Okay, go ahead and tell.
All right. I'll start the test running and I can show you the pass. So we spent a lot of time talking about the velocity machinery we want to add. We're adding to AstroPy, which is to support the case of my spectrograph is pointed there. I want to know what the radial velocity offset is of my observation. And we spent a lot of time talking about how that needs to work, how that fits in, how that will fit in with the coordinate framework. And then we spent a fair amount of time hacking on just getting sort of the baseline implementation to work, right? The sort of simplest examples we could come up with using 2 different methodologies that let's not dwell on right now. But let's see, let's start the tests running and we'll see whether they're done in a minute. Adrian got most of the way there, right, with the matrix technique. Is that true?
Yeah.
And literally 1 o'clock yesterday morning, I got the test to pass on the velocities stuff.
Ooh.
So, or on the differential version of it. So that strongly suggests with just a little bit more finalizing work, this can actually get into AstroPy as opposed to being this sort of experimental thing that Adrian and I have had floating around in our heads.
Yay.
If you want, the tests are going to take a lot of runs. So that's fine.
Okay. Cool. Code review.
So it wasn't just me, but so it was my first review ever. My code, first thing that someone else saw it, and Francesco and Duncan and loads of other people gave me loads and loads of great tips, taught me about exceptions, zipping, enumerating, things that I should probably know, but that I didn't.
I guess we just talk about that. But
Can I just show something? Like,
yeah.
So basically, you've already heard everything about the regions package. Some of the things that Johannes mentioned will be in the next release. So we actually coded yesterday. But if you're interested in seeing, let's see. So I can't. Okay. So this is the main documentation page of regions at the moment. And so as part of the work yesterday, we refactored a lot of the kind of functionality, DS9 reading, we implemented a lot of missing functionality, but also I tried to tidy up the documentation. And so if anyone is interested in reviewing this, I've actually, sorry, I can't do this. There's a preview of what the documentation would look like with the new version. So if anyone wants to go through, I mean, it would be really helpful to have, fresh pairs of eyes just looking through this, seeing if anything is unclear, and then we're trying to merge these things in and make a release at some point soon.
Cool. Yay, documentation. Yay. All right. AstroQuery.
So we have a number of independent things on here, so
okay.
Best to go through each bullet and ask that person.
Okay, so I guess Edward Gomez?
Yeah, so
do you want me to click on this?
Not really, no. At iAstro 2 years ago, I put Last Congress's archive into AstroQuery, and we changed how our archive was stored and where it was stored. So that was totally broken a year ago. So I fixed that, and but all the tests are broken. So unlike Eric, I can't show you a test myself. But I have issued a pull request for functionality, which includes object lookup within a specified date range and authentication, so you can get your images of a particular object within a particular date range.
Yay, new data. All right, Adrian?
I started a sub-module for the CDC. I did a remote data test where I was able to query our database and retrieve records. I'm about to finish the unit test and hopefully issue a pull request to finish this and the documentation.
Awesome. What's up? Azali.
Okay, I just went through the documentation and copied and pasted the examples and checked that they worked and that the output matched, and when it didn't work or the output didn't match, I fixed it. So I got through like the main landing page and the synthetic examples.
Cool. That's really important to make sure all the examples in the documentation work, because that's the first thing that people try out. So thank you for doing that. Carol.
Can I?
Yeah.
So it's
because pictures are better than words, especially with my accent. So the fact is that when I wanted to help to hack a bit of astrocarry, it appears that I was a bit too new for that, and that the best was to try to apply it for the script I was working on. And it appeared that the really first astrocarry request I needed didn't exist. So now, if you need it, in Sinbad you can retrieve for one object. You have a list of publications associated where it was quoted. So normally, like on the website, it's not an issue to get them. It didn't appear actually in astrocarry, so it's almost available. If you really need it, it's under my own repository, and it should be soon, hopefully, in the official astrocarry. And I think also, I mean, like it's something, I don't know if it will be under astrocarry or something like that, but it gives me a lot of tools to maybe try to carry directory the journal. So for example, my main goal is to retrieve maps from a given publication. So we can imagine that at a time for one journal we can just pass a comment, and it should be something quite easily, we can script it quite easily. Like once we are in a journal and we understand how it works, it should be easily scripted for each journal. And after that, we are just limited by the imagination. And one thing I would like to take time to underline, it's really like the help of each of you. And yesterday was particularly showing this example of all the we get to. Like my code is really 1.5 line of functional code. The rest is actually the works of Brigitte and Adam that actually put a lot here. And also take the time to debug a couple of things that I was doing wrong. And of course, like the whole week, put also here a lot, and I'm really thankful for all of you. Thank you.
Cool. All right, and then Esteban.
Yeah. So I added the Vista database to AstroQuery. So far it's within the UKIS class because it's very similar structure of the website. But maybe in the future we can separate this class. So yeah, so my local tests I worked, and maybe my first real pull request.
Yay! That was a lot of work on AstroQuery yesterday, so that's cool. Cool. So Astrobot. Ooh, sorry, that was too far.
Yeah, so I didn't work at the end on Astrobot, but tried to work out the page speak, which still doesn't speak to me.
Oh.
So failed hack, but I haven't given up. And the other hack I'm doing all week is to set this challenge to get the AstroPy open issues under 700 and the open pull request under 100. And I think that challenge is almost met. Don't have issues. No, but a big thank to Fabian, who is not here, and close and merge loads of pull requests and ship ones. And the only reason the challenge didn't get met because also a weekly, and it is one of our busiest week in terms of opening and closing.
I'm just gonna
maybe not the number of nice in
26 merged, 40 closed issues.
Does it?
So those numbers are really
that's cool.
There you go.
The best part was having some in-person consultations with Tom and Eric to figure out exactly how we should do it.
Cool. And okay, awesome.
Lucia mostly. So there is a link of a document I'm trying to write. So yesterday we got the overall, it's a 3 pages. So the overall structure. And I will try to update it with some more examples of commands you can run and trying to get a bit more fluent. Probably would be very nice if anyone that speaks English better than me give a read and try to translate from Italish to or a German and Italian hacking this together. So might be some weird contrast.
Is this in the Pastor 17 folder?
Yes.
Okay. So also anyone who wants to learn about virtual env and stuff, this is now a good research to look at.
And if no one has anything against, I might try to make it as in my first ever post.
Very good. Cool. So thank you for that. Okay. Visualize simulated stars.
Yes, so this was a tool that I already had, but I've tried to make it a little bit more user-friendly, combined with another tool that I had for creating a simulated cluster, so initial conditions basically for simulation. So I'm trying to add a GUI for both of them and maybe combine them, but so far I've only added that to the generate a cluster thing, but that seems to work. The other tool, the visualize the cluster tool, that now works without too many troubles, but it's not quite done yet. But I did add a sample image, so if you can click on that, you can see what it results in.
It's very pretty. I like it.
Ooh. And are these now simulated stars?
Yes.
Cool.
So this is basically what that star cluster that I generated with my initial conditions would look like if you would look at it with Hubble.
Cool.
Very cool.
Awesome. Awesome. Telescope pointing report generation.
Yeah, so it's probably a generator. But so I hack a bit on the matplotlib and PDF generation generator, and it seems to work. I need to do a lot of other things in the code which translate the use of the subplots to feature and better understanding the axis in the matplotlib, so you can see in the GitHub, and you can get nice results from that.
Is there something to click on? Or
yeah, if you click on
this one?
the example report, you go to reports folder, click like 1 meter first, you'll get some nice graphs in PDF.
Oh, nice.
Scratch that.
Ooh.
It's very easy to do those kind of graphs if you have data.
But they look pretty.
Yeah, they do.
Awesome. Okay. X-ray responses. Hey, that's us. Hello.
Yay!
Okay. Do you want to say something or?
Sure. So there were kind of two parts to this, so I guess Leah can say something as well. So what I was working on mostly, and Daniela a bit, was finding a way to account for the instrument response in the models, so that you can fit your models to your data using whatever fitter you want, whatever models you want, and doesn't have to be in the like clunky XSpec interface. So Daniela already got this working for one of the instruments on Chandra, and then I helped out with getting it working for RxTE, and then I played God and faked a bunch of data for other RxTE and Nicer and EXTP, and Daniela got it working for all of those. So we're on a roll.
It works.
Something's happening. Yeah.
So I helped some with the ARF stuff and RMF stuff for Chandra, and wrote like a class just for dealing with the data files. And I also was working on wrapping C++ code. It ended up being massively annoying because thanks to Kyle Barbary for figuring out how to convert numpy arrays to val arrays in C++, but unfortunately it doesn't work on every machine. So it works on a Linux computer but not a Mac computer, which I think is why people don't like Mac, C++, and Fortran compilers, because it seems to be sort of like black magic. So we might try another thing in the future, but for now we have like a basic C wrapper that, well, you can click on the second link. You can see Kyle's example, which is like pretty clean. So that will work on some machines. And yeah, so more stuff for the future.
So this is now an example of how to do a val array to connect it to
Python.
Cool.
Yeah.
So that might be useful for some people.
Yeah.
Cool.
Yay.
Let's close some of these links. Packaging Python module. Make it available on GitHub to install.
Actually, yesterday I made my first Python package, tried to make it, and I got some success. But I have to check it whether it is installable for others also or not. This is a simple Python module for angle calculation. This conversion in between degree radians and degree minute second, and addition of two angles and subtraction of two angles. I put it on GitHub also.
It's there. If someone wants to try it out, whether it installs, then you can do that. But congratulations on getting your first package. And there was another one. Anna.
Yeah, I tried to put the code that I present on Monday, the 30th, available on GitHub on Python, and I tried to put it in Conda, but it failed because I want to be very ambitious, and I forgot I want to put the data example for SDSS, so I have to make some sense, change it, and then it will be available.
But it's now all online.
Yeah.
Yay! Cool. Packaging and cookie cutter.
Click the demo.
Demo. There's a demo. Oh wow. Do you want
Click that. Do it full screen. Oh. Alright. Don't see if I can. So we got as far as this, basically, where we decided to call the package piece of cake because why not? It asks you a bunch of questions. Hack day. And then when it gets to the end of asking you a bunch of questions, it asks you what license you want. It's very important. And then it renders the AstroPy package template for you with the settings in a local directory on your computer, which is what it does there. So with all your things, and then it will ask you whether you want to create a new repository on GitHub. You can type in your username and password, and then it will crash, because that's as far as we've got.
But it's in the works. And you said some package did get.
Yes, we used Fuss to test out the current version of the cookie cutter package. So me and Eloise went through setting up that package and putting it on PyPy and installing it. So that was
So new package.
New package.
Yay! Okay, the bus factor.
Yeah, click on the presentation.
I will click on the presentation.
Yeah, so.
I'm working on it.
Okay, so. So yesterday we were working and today, my God, to 3 in the morning, we were working on the bus factor. The bus factor is how many people are dependent in your project. So we tried to write something up, and that's what we got. For example, for SciPy, we got like from 13
1,365 files, these like almost 30% of them are not good. I mean, that's only one contributor to that file, and that's removing all these init files, the tut package, all these files that don't want to use it. And then on the bottom here we have who are the users, and by the color, how many years they haven't appeared in the project. So there's this Yarrow Mailman in SciPy, which has been like almost 250 files, and 8 years that they haven't appeared on the project. Most of them are staying like Fortran packages, Fortran files.
Wait, that's years they have not appeared?
Yeah. He hasn't commit in any other files.
So he wrote 250 files and hasn't done anything for 8 years?
Yes.
Okay.
Not the other way around.
250 files that only him touched.
Only him. He's the only person who touched this file.
Okay. I don't understand the color bar.
The color. This is years.
Years.
Yeah,
Since last
1, 2,
commit.
3, 8
Years
years.
since last
Just write a label on the bottom of it.
Yeah, sure. It was 3 in the morning. Next one. So we went NumPy. NumPy, we got like, oh, that's almost 9%. And most of the people that have more files is still contributing. So in the last year, they have contributed, even though Travis hasn't contributed for 8 years, no, 7 years in this case, and has like around 5 files, which are okay. Yo, you can talk about AstroPy?
AstroPy, yeah. So we have this guy, Michael, which is like 2 years that he doesn't show up. And he has 25 files, basically.
It's not that he doesn't show up.
It's since last commit.
The last commit, he hasn't contributed to the code base.
If he has to show up, or if he hasn't.
Are they live?
We don't
know. Now, AstroPy, we have to
He's
compare.
alive, but he's dead to us.
SciPy, which is a small code base, like 225 files. We have Nabil. What?
That's not right.
That's in master.
Oh, it's in master.
Yesterday,
Okay.
so you haven't contributed for 4 years, even now you're releasing the code, so good. Okay, well, so then we got more to file utils. That's yours.
I haven't seen this one.
What numbers are those?
Wait.
That's you.
Yeah, but
0.14. Good. Let's get that's all. That's the last slide. So that was all that we managed. It's all in the package. It's called Bus Factory. It's in the link. You can try to run it in your Git repository. Still tricky, and there's a lot of things to change if you want to improve it, because there's a lot of issues that we could make it better. So
just do pip install -e dot inside the bus factor
You guys have a question?
and then use bus, the name of the
I
group.
don't understand what not okay, like what.
Oh, only one contributor has touched the file.
Okay.
No, okay.
I have a comment and no
Okay.
questions. So it shows that the case is not that bad for AstroPy, but I think the real case is much worse, because there are like me, I'm touching many other files with Pepate and stylistic and typo fixing, automated stuff, but that's not real contribution to those files. I mean, I still don't understand what's going on in that module, and that doesn't show up.
So this is the best scenario.
Yes, so that tricks all the statistics, so the reality is much, much, much worse.
So you can play the system.
So now we have to run machine learning to figure out what people actually do.
This is
exactly.
take a ratio of, if a person contributes like 90%, that's still the last factor.
Cool.
Okay, cool.
Yay. Very nice. Where is paper globes?
Yeah, well, turns out it's really difficult to multi-see one in 3D and then project onto its faces. So we're still working on it. I'm working on it right now.
Can I click on the paper globe output thing?
Yeah, it doesn't really show much.
It doesn't show any coordinates or anything on it, but it does show how you printed the 20.
Okay. If anyone needs to print a D20 for their next D&D session,
We've come up with a cool framework. I think we have a nice structure to the code, for the class, it should work, and it's all. It's sort of set to, keep working on it, which I will do because it's something I want to do anyway. So.
Cool. So sometime soon in the future, you can make D20s with fun images on them, which is awesome.
Yeah.
MC.
Yes.
That's a lot of M's and C's.
I updated my code to use MC for the MC from PyMC. Mostly thanks to Daniela, who helped me a lot. It's now running and it's working out, and I'm currently testing different chain lengths and different priors to see if it's all correct. But it seems to, and I'm going to chat about this with Eloise in the coffee break, so if you're interested, come by.
Cool.
Nice.
SpecVis testing by using real data.
Yeah. So the idea was there is this new package that is already online. So I did the installation following the steps that I already described. And there was some problems in the when you use Conda. So there was a very specific NumPy version. So I was stuck like half an hour with Francesco helping to going on. Later on, I upload some spec that I have, and I was actually, I mean, it's, you can put layers that you can fit models, and there are, I mean, you can fit Gaussians, you have Lorentz profiles, actually absorption Gaussians. So it's really, and I already did the measurement of the equivalent width. So I compared with some measurement that I did before by using other software to check if the prediction are good or not, and it was the one that I'm doing now. And I found something that can be improved, because you can just upload the spectra, but if you have a variance file or the skylines, you can do it at the same time. There are software that you can see the both, so you can compare, and you can also upload a data file of emission lines, absorption lines to get the redshift. So there are some improvements that I would like to contact the person developing, if it is possible, for example, to upload this emission lines table, so you can get the measurement of the redshift based on the lines.
Very good. I think many of us have already noticed the Riot bot for voting, but
yeah, so the bot is kind of a collection of loosely related bugs. But it takes some input and keeps a tally of votes. I'd like to improve it a bit more, but it does a thing. I'd also like to give it a slightly better name, so if people want to have their input on that, we can use the bot to name the bot. So I'll stick you back in the
but we
My
can.
god face.
Pardon?
No.
Can't see my god face.
But we can now vote on Matrix, so yay! Ooh, help. A baby step toward on modeling lunar occultation light curve.
Okay, so what I was trying to do is to incorporate all the knowledge here. So I tried to create some simple program, simple code to modeling lunar occultation light curve, and then make a Jupyter notebook for that, and put it into GitHub repository.
Ooh.
That's all.
There's a notebook there, and it's open source, so very good.
Thank you.
Yay! All right, solar. Ooh, help. Solar eruption data visualization.
Yep, that's me. So I pretty much set out what I wanted to do. I had 2 telecons, so I didn't have loads of time, but I did check out the documentation for some of the data viz things I've seen this week, installed them, and then got my data catalog working with them, so I got it loaded in. There's more stuff I definitely want to do with it. I think it's going to be really useful. So I need to get the signs out of the scatter plots now that are there. But yeah, good start, it works. So.
Cool. it's WCS to GWCS prototype converter.
Yeah, I was able to get something working on the couple simple examples people sent me. So.
How much data did you get sent in the end?
Well, 2 files basically.
Okay.
Well, three. One was spectral, and I didn't do that one. But I'd like to today. I'll put in support for SIP distortion. But yeah, it handles simple tangent projection. I think.
And it works?
It seems to.
Yay! Okay, AstroPy website reorganization. That sounds like a big thing. Ah. Okay.
Okay, so Kelly started a lot of this work, and we currently have pull requests in, but that means you can't see the changes we've done. So,
Well, so I want to start by saying, so my intention was to work on the AstroPy tutorials, and then I sat down with Ekaterina, and she said, and we were like, okay, so try to find the tutorial. She Googled AstroPy, got to astropy.org, and there's no link to the tutorials. So then it took a little while. So then basically the hack changed to improve the visibility of the tutorials, which then changed to update the webpage.
yeah, so when I joined the project, I think the big issue we were trying to address was that there's a lot of duplication between the HTML website and the Read the Docs website. And so how do we get rid of that duplication so when you have one place to update it and improve kind of the visibility and usability. So this is our new prototype website. It just simply has what is AstroPy, how to install it, a link to the examples, tutorials, documentation, how to get help, and then how to report bugs, and if you want to support us. My big learning was learning how to make a drop-down menu in CSS. So all of this information, the team was one of these top things. Docs wasn't a top thing. And the code of conduct was in the about, and how to acknowledge AstroPy was in the about. So we made this menu, moved docs up there, and now you can see about AstroPy. We consolidated the information on the AstroPy project, and then talked about the core, the affiliated packages, the licensing, and then our fiscal sponsorship, and everything else is there. So. Do you want me to bring up your?
Actually, so yeah, I made it. If you could click on that image, yeah, perfect. Now I'll drag. So this was the before, which it wasn't terrible. It was just like things weren't quite where we expected them to be, and they were organized differently than on the HTML. So getting help. This is old, this is before. Getting help, reporting issues, and contributing is now all moved and not duplicated on the astropy.org site. And so this is on the new site, on the new Read the Docs. It's linked in this new Getting Started. And I think that's the big thing. So now when we say Getting Started, we point people to the example gallery, the tutorials, Get Help, which just lists all the discussion forums, and then one Contribute Data and Report Problems, which is issue reporting. I think some of the stuff that was in the Getting Started before is now in this Import AstroPy and subpackages and Getting Started with subpackages, which has some detail. If you like this, there's a button you can thumbs up it, so that then maybe the other maintainers will approve my pull request.
Kelly faced the pull request workflow in a way that she was not expecting.
Yes, that's true. That was part of the hack, was learning the PR workflow. Was that there are lots of comments.
People have opinions.
No one has expressed any comments on the new HTML, so I think they're all busy with Kelly's.
Conda packaging.
Yeah, so I was able to successfully conda package one of my projects. So now you can install that via conda.
Kyle?
Yeah, I did the same thing. I moved with a package that Matt had on the Open Astronomy channel to Conda Forge and preparation for moving everything there, and made some headway on doing the same thing for SM Cosmo. Where's Matt? Want to say more about packaging, other stuff?
Sure. So as a few minutes ago, I can now check on the Conda Forge channel for
and I finally made some headway on fixing that. And that's been something I've been procrastinating for like a year and a half.
Cool. Yay. Convolution.
So I spent a large fraction of the week trying to finish off a pull request that started a while back, following Brigitta's lead, and it turns out to be very involved. But one of the things that's changed is the documentation there. So the link is to the compiled version of the docs from my pull request that shows a few examples. Yeah, bring that up. If anyone has any feedback on this, the figures are the interesting part. This just shows what the AstroPy convolution does as opposed to sort of the normal SciPy one. It interpolates over NAND. If anyone has any thoughts on better examples to include in the docs, or wants a review.
Implementing my own standalone script software development party.
Right, so this is a script that I've been working on with a couple student collaborators, and it was not modular or tested or anything, and I made it those things. If you want, you can do the sample plot just kind of show what it actually does. It basically, we have a bunch of apogee spectra that have a bunch of telluric garbage, that's the blue, and we want to get rid of the spikes that are not data and then be left. And it did.
More AstroPy velocity.
Yeah, so Eric made me look bad. So in between when he spoke, I then fixed my part of the velocity transformation, so that now I successfully ran a test that converted from a galactocentric position and velocity to ICS for him. So
Yay.
That's a good thing.
Also, my test passed. You can see it at the next one.
That is true. Yay, passing test. Thank you so much, everyone. I feel like there's a huge amount of work that got done in just a single day, and that's kind of amazing. I have one more hack that I worked on that I need all of you to help me with, and that's the PyAstro 17 survey. You should, in the next, actually not right now, but you should in the next few minutes get a link to a survey. Please, I think we'll maybe have some time later to have like 10 or 15 minutes for you to fill it out. Please do that. It's immensely helpful to us to know what worked and what didn't work and what we need to change, because we're still working on the unconference format and how to make that useful and fun to all of you. So please help us by filling out that survey once you get the link. If you don't get a link I think we're a bit late.
Yeah, we're on until 25 to.
25.
No, say quarter to.
All right, we have coffee until 11:45.
So, like 20 minutes.
Yeah, no, I found the chain. The question was just, is that the best way to get there? Yes. Like that's better. Yes.
Oh, okay.
Yeah, I found one that's, I found like 50 trains. There is no way realistically to get to the train station of the taxi.
I don't know how the buses work.
Oh yeah, about the
There are the timing doesn't work out. Like sometimes you have to wait for 40 minutes.
Yeah, that's sort of
like the night buses only run once an hour. And so I don't know how early they're going and how the night buses work. Sometimes there's like a 5 a.m.
It's a total hack. Trace routing down to actually gave them the specific key, and the gateway name is called Hub Gateway.